Hello everyone, welcome to Pepcoding. So in this video, we are going to start a new question of our tree series. Okay. So the question that we have this time is in order Morris traversal in binary tree. Okay. So we already know about in order traversal, right? But what is this Morris traversal? So let us see what is this, and after that we will discuss that how to do this question. Okay. So what is in order traversal? First of all, let us see that as we all know. Okay. In order traversal is we did this with the help of recursion. So what we did is we called first one left call. Okay, the left call first, then some work like printing between left and right call. Okay, it is my right call. So we have two calls, first is left, first is and second one is right. So in between that, the work that we are doing is in order work, right? And in this work, if we are printing the nodes data, okay, if we are printing the data of our nodes, then that will be called as the in order printing. Okay, so suppose how I'll start is, what I'll do, I'll start from here. Okay, this is the left call has started from here, so it will go to the left of the tree first. Okay, so left will come here. Okay, first of all I'll come here, then I'll go to this node. Okay, and after this it will make its left call, and it will say that the left is null. Okay, and after this it will come here because it will return from here when the null will encounter, when it will encounter a null pointer, then what it will do, it will print this. So 2 will be printed first. Okay, so 2 is printed, and then uh the right call will also say that it is null here. Okay, so now it will go to 7, it will go to 7. So when it will go to 7, then the left call is already been completed for 7, right? Then after this, now the 7 will be printed, and the right call of 7 will take place. So here the call for the right call for 7 will take it here. Okay, I'm at 6 now. So after 6, what I will do, I'll first make my left call. So left call here. Okay, 7 is already printed, left call here, and then we will reach to 5. Okay, and after making the right call and the left call of after making the left call of 5 will print itself and will make its right call. Okay, and after making its right call, it will go to 6, it will go to 6 again. And as we already know that the left call is done for 6, so 6 will also print itself, and then it will make its right call. So right call will take it here in at 11. So after coming to 11, what it will do, it will make its left call first. Okay, print 11, make the 11 right call of 11, and after making the 11 right call, it will go to this 2, right? This 2, so it will come here. So after coming here, the left call for 2 is already been completed, so 2 will print itself first and will go to the right now. Okay, print and will go to the right now. So after coming to the right, it will first make its left call. Okay, the right call will take it here again. Okay, back to the, suppose it is my function in order is the name. So it will, what it will do again, take it to the left call. Okay, and when it will make the left call, then it will return from there, right? Because it is left is null. So it will come back here again and will print first of 5 will be printed first, and after that the right call will take place. So right call will take it here. Okay, now after this, what it will do, it will take it to the left. So it will come here, right? It will come here, and after making its left call, it will again print 4. Okay, and then after printing 4, what it will do, it will make its right call and will take it to here at 9. So left call is already done for 9, so 9 will also print itself, make it right call again. Okay, from there it will return, and then this is how it will be completed. Okay, so this is my in order traversal. This should be printed when I will complete this question. Okay, this should be printed. So but in this question, what I will do is, I'll not take the help of recursion or any extra space. Okay, I'm not going to take the help of recursion, because this time I'm coming back to this 7 with the help of recursion, because it is returning from here. The left call is being exhausted, right? The left call is being completed. Now for the right call, it will come back to 7, and then it will make its right call here, right? For this node, I'm saying that I'm going to 2 first. Okay, and when I'm saying that I don't have any call in the left round, okay, I don't have any call in the left side, so I'll return to 7. And after returning to 7, what I'll do is I'll go to my right, because I have one more right call left after printing. Okay, printing, and then I have one more right call left, so I'll make the right call now. So this is how I'm traversing in pre-order. But I cannot do this in this question, because in this question we are going to learn a new technique that is Morris traversal. Okay, that is Morris traversal. So what is this Morris traversal and how is it useful and why we are using this, as we have already learned the Inorder traversal by recursion. So why we are using this, why is it important? So with the help of Morris traversal, what we can do is we can print the Inorder. Okay, in this question we are going to print the Inorder. In next question we are also be printing pre-order. Okay, so we can print Inorder with, we can say, without any extra space or without any recursion. Okay, without recursion or without extra space, we can traverse into this tree. Okay, and it is so cool that we are not using any extra space, right? Because in recursion also we are using extra space of stack, right? Let us make the stack first of all. Okay, let me show you that how the stack is filling in pre-order for in recursion. Okay, in order of recursion. Okay, so let us see. So first of all, here what I will do is 2. First of all, I will be at 2, right? So this is my recursion stack. So what I'll do is, first of all, it will make the call for 2 left, right? 2 left call will take place first, and then it will go to 7, then 7 left. Okay, and then 2 left. So left, then print, and then right. This is the order, right? Print, right, and these are calls. So these are calls. So what I'll do is 2 will be printed now. Okay, because the left call is being completed for 2, so 2 will be printed first. So 2 will be printed, and after that it will say that make my right call. So 2 right. So after making 2 left and 2 right call, okay, the right call of 2 and the left call of 2, it will say that all the calls are completed for 2. You can come out of this stack. So now it will go to this position. So now we are at this, right? 7 left call is done, so we will print 7 first, and then we'll make 7 right call. Okay, we'll make the right call of 7. So right call will take it to 6, right? So now what will happen is 6 will say that make my left call. Okay, so make my left call. So left call will take it to 5. So 5 will say make my left call, 5 will say print me, and 5 will say make my right call. Okay, so this is what we will do for 5. Okay, and as the both calls are completed for 5, so 5 will come out of this stack. Okay, or we can say that 5 will be raised from the stack. So yeah, so now 5 is printed. Now we'll reach to 6. Okay, the left call is done for 6, so 6 will also be printed now, and the 6 right call will be made. Okay, 6 right call will be made, and we will reach at 11. Similarly, 11 left and 11 right, 11 left, and then printing 11 and 11 right call will made. Okay, these two call like first left call, then printed, and then right call. Okay, this will be done, and then 11 will also be erased. 11 will also be erased. Now what is happening is, see, it is done for 11, right? So now it will go to 6. So when it will go to 6, 6 will say my both call are completed. Now what I can do? So simply you can come out of the stack. Okay, so now it will say I'll go back to 7. So 7 will say, okay, I'm also done with both my calls. So what I can do now? Nothing. You cannot do anything, as you are done with both of your calls. So it is also erased. Okay, it will also be erased. So this is how my stack will look like now. Okay, so I'll come to this position, and then I'll go to right, because it will say that I have a right call left. So 2 right. Okay, now 5 will make it left call, but it won't get anything, because it does not have anything in the. Okay, first of all, after this it will print 2. Okay, print 2, and then we'll make 2 right, and then 5 will make its left call, will not get anything, and then print 5. Okay, it will print 5 and will come to 5 right call. After printing 5 right call, and then it will say, it will come to 9 left. Okay, 9 will make it left call. So after making its left call, it will say 4 left. Okay, 4 left, and then after 4 left, this will be the 4 left, right? So after 4 left, 4 will be printed, and then 4 right call will be made. So when we'll make the 4 right call, okay, the right call of 4, then after that it will say that I'm done with both my calls. So it will say come out of the stack. So now what it will do is it will print 9 as it will reach to 9 this time, right? Because left call is done for 9 printing will be done, so 9 will be printed. Okay, and after that 9 right call will be made, and it is null, so both the calls are completed. So it will also come out of the stack, then it will go to this, right? Then it will go to 5. So after coming to 5, what it will do, it will go to this 5 is also done with both of this call, and it will also come, and 2 is also done. Okay, so this is how the stack trace will look like at the time of pre-order. Okay, we can see that we are using stack continuously. Okay, we are first making 2 left call, okay, left call of 2, then left call of 7, then left call of 2 again. Okay, so this is how we are filling the stack. But in Morrison Traversal, we are not going to use any recursion, so we are not taking any stack space. Okay, any space of stack, we are not going to use it. Okay, again, second thing, we are not going to take help of recursion. Okay, so no stack will be needed now. Okay, and nothing, no else data structure will be needed. Okay, not even array. Okay, and but that is different, that if we need to return the answer in the form of some array list or some vector, okay, so that is a different thing. But in this, we are not going to use any extra space. So this is why this is so much important. Okay, this is why the Morrison Traversal is so much important. So how we can do this Morrison Traversal? Okay, we have already discussed about this Morrison Traversal. Okay, why is it important? We have already discussed it, and the concept behind this is, we can say, threaded binary tree. Okay, threaded binary tree. So what is it? So let me give you a little gist of this Morris Traversal, right? Let me give you a little gist of this. So what will happen in this is, in this case, what we will do, see, we are not going to use any recursion here, right? So I'll be traveling from here, I'll go here, then I'll come to this, but when I'll come to this, I cannot now go back to my children. I mean, my parent. I cannot go back to my parent because the link is from parent to children, not from children to parent, right? So how I can go back? So this is what I need to understand first of all, because if I need to traverse in order, so in order cannot be changed, because in order for a tree will be always look like 5, then 6, then 11, then 2, then again 5, 4, 9 will always look like this. Okay, the tree, the in order will also always be same. Okay, this will not be changed, and but what will be changed? The techniques for printing this, the techniques for printing this will be changed. So now the technique we are using is Morris Traversal. Okay, so the technique which we are using is Morris Traversal. So how we can do that is, see, so so already told you about this problem that we are facing, that if we are not using recursion, then I cannot go back. Okay, so how we can do this? We need to find a solution. So see, if I have a link from this to this, so can I go to this? Yes. Suppose if in the right of this 2, I'll attach this 7 somehow. Okay, I'll attach this 7, so I can easily reach from here to here, right? So this is the first thing what I need to do. I need to make some connections. So similarly, when I'll go here, so I can come here as I have link, but when I'll come here, I cannot come back to this, so I'll make again a connection here. Okay, and now from here I can come here, right? And from here I again have to make a connection so that I can go to this two. Okay, now from here no needed. Okay, it is not needed. Like I'll reach here, then I need to go there, right? And then I need to go here. From this to this I can go easily, right? But from here to here again I need a connection. Again I need a connection. So this is how I can traverse a tree. How I can traverse a tree? See, we have connections, right? We have these connections from 2 to 7, from 7 to 2, right? So I can travel from 2 to 7 to 2, right? 2 7 2 I can travel, but I need to go from here to here. So for that I need to make connection. So suppose I made a connection from here to here, I can come, from here to here I can come, from here to here I need to make a connection. Similarly, from this to this I need to make a connection, and from this to this also I need to make a connection. So if I traverse this now, see, can I traverse this tree now? Okay, I can traverse this tree now. So this is how it was just a gist that we are going to use in this question. Okay, it was just a gist of this. So but if we'll keep this connection as it is, right? If we'll keep this connection as it is, like I'll join this 2 to 7, so my tree will be changed, but I cannot change the data that I have, right? So I need to think about that also. So this connection that I'm making right now are threads, are called threads. So this is what the threaded binary tree is. Okay, this is the concept of threaded binary tree, that I'll make some threads to join my nodes so that I can traverse into this tree. Okay, so this is the concept of threaded binary tree which we are going to use here. So I hope that you understand this threaded binary tree, and let us see that how we can do this Morris traversal. Okay, how we can do this Morris traversal. So first of all we will understand that how we can do this. Okay, and then we will see the code. Okay, and then we will see the code, and in code we will again see that what we have discussed here. Okay, we will see that what we have discussed here, we will write only that. Okay, we'll write only what I have told you in this dry run. Okay, we'll write the same thing in our code. Okay, because what happens is, when we understand a code and we understand the dry run, then it is quite easy to convert it into the code. Okay, it is quite easy to convert it into the code if we understand the dry run properly. So we will focus on dry run first. Okay, so let us start. So I'm discussing how here. Okay, I'm discussing how we can do this. So what I'll do is, I'll put a pointer here. I'll put my current pointer here. Okay, so what are the conditions when I print in my Inorder? What are the conditions? See, I traverse this way, from this to this to this, and when this side ends, when this left side ends, this is the first member which will be printed. So first of all we need to understand that when the left side will be ended, when there is no node in the left side, no node in left, then at that time this member will be the person which will be included in my Inorder, right? So it is done, right? It is done. We understand this. And now this thing, if we have traversed this side, we completely traverse this side, this subtree, then at that time we are going to add this into our Inorder, right? Suppose if we have processed this subtree, we have completed this subtree, then we will add this two, right? So there are two conditions: if there is no node in the left, okay, and second is if we have processed the left subtree, then in these two conditions we are going to add or print our node data. Okay, so these are the two conditions. And otherwise we always go to the left side only, right? We never go to right. We only go to right in the two conditions, that is, when the left call are exhausted, we go to right, right? When left calls are exhausted, we go to right. And then the second thing is, we go to right when the left subtree is processed. Left subtree is processed, go to right. Okay, left calls are exhausted, go to right. Left subtree is processed, go to right. So these are the two conditions. Okay, So this is what I need to do. So what I'll do is I'll keep my pointer current here, okay, and I'll make a left node. Okay, I'll make a left node to the left of this current. Okay, and then what I will do is, I already have told you that for traversing this I need some threads, so I need to make some connections. So how I will do this is, see, I'll place a current in the root first, okay, and then will place a left node to its left. Okay, and what I'll say this to this left node is, I'll say give me the rightmost node of this left node. So what it will do, it will give me the rightmost node, that is this. Okay, ln will come to this, okay. I'll write this cross to mark how many times it is visited. Okay, it is visited first time, it is also visited first time, then one this and one this. So when I came here, okay, when I came to the rightmost, I need rightmost node. Okay, when I have this rightmost node, let me write the steps properly. So I need this rightmost node. Okay, so after this rightmost node, what I'll do is I'll check if the right of this rightmost node is null or not. Okay, if it is null, then that means that there is no connections, that means there is no connection, right? If the rightmost is null, that means there is no connection to this. So at that time I'll make a connection. Okay, at that time I'll make a connection. We are understanding just how only right now. Okay, and why we will discuss this later. Okay, why we'll discuss later. So let us concentrate on how first. Okay, so how it will be done, we'll take a pointer at the root and then we'll place a left node to it. We'll take out the rightmost node and we'll make a connection to its current, right? So after making the connection, what I'll do is I'll shift my pointers, that is this left node and this current, okay, to the left. Only current will be shifted, right? Because see, after shifting this, I make my left node to the left of it. Okay, now I'll create my left node. Okay, I'm not shifting both of them, I'm just shifting one, and what I'm doing, I'm making one left node to the left of it. Okay, so that is what it is. So here we can see the left node is not null, right? At this point, when the left node is not null, see, I'm writing here, when left node is not null, not equal to null. So at that point, what we did, we need rightmost, and we checked if null or not. Okay, so this is what we do. We placed a left node. Okay, we placed a left node, and after that left node we checked if it is null or not. Because see, you will say that where you have checked that if it is null or not. See, I'll do see, in this case, here I have C, here I have left node, so the rightmost node is this only, right? I need the rightmost node of this left node, so the rightmost node for this left node will be this only, right? So I'll make a connection again. If there is no connection to the rightmost of right, I'll check if the rightmost of right is equals to null or not. Okay, rightmost, I'll take out the rightmost and I'll check if rightmost, right of rightmost, where I can write it, rightmost right. Okay, I'll write it here. Okay, if the rightmost right, see, the right of rightmost is null here, right? The right pointer of right, it was the rightmost, and the right pointer of it was null. So when it was null, I make a connection. So here it was also null, I made a connection, and after making the connection, shifted. Okay, shifted. So it was visited first at this time, and now second, the C is coming here. Okay, C is coming here, and again it is also visited 2 times. because of ln, and then c will come, c also came here, so it is visited 2 times. Now when we will create our left node, so left node will be created in the null, right? Because left node is created to the left of current. Left of current is left node, right? Left node is left of current. Left node is left of current. So now it is null. So when it is null, I can see that this time my left side is already being completed, right? Left side is already being completed. So at this point, I'll add my current data. I'll add my data of this current pointer. So the data is at this is 2, right? I don't have anything in the left. So what I'll do, I'll add this to my this, I'll print it, okay, or I'll add this to anything like any vector or array list or any array in which I want, okay. I'll add it, and then after this what I'll do, after adding this, I'll make the call for the right. So now I'll say that I have established the connection before, okay. I established the connection, that is I established the connection from the right of this to current to this, right? So what I'll do is I'll take this current to the right of it. So after this will be moved here, this will be moved here, okay. So if you are not understanding this right now, okay, so do not worry, because we will do more iterations, and after 1 or 2 or 3 iterations you will understand it, okay. So here it is visited the third time, okay, it is visited third time. So again the same thing, make left node, take out the rightmost node. So this time rightmost node is 2, right? It is also visited third time. So rightmost node is 2 this time. So when rightmost node is 2, we'll check the right of rightmost. So right of rightmost is current again. So this time what I'm saying is, I'm saying that right of rightmost is not null, right? Right of rightmost is not null. What that means? That means that my child can access me. My child can access its parent. Right? Here we have the access of its parent, but it doesn't happen in tree. The child does not have the access to its parent. So what will happen? What is happened here? So at this point I can see that I already have visited that side. I already have completed and processed that side. So I will add it to my tree. I will add it to my in order. Okay, that means 7 will be added. It is too much of hodgepodge. So I'll not write this here. I'll write this. I'll write this here. Okay, so what we had 2, and now we see the left side is processed, so we will make 7 again. Okay, we will again add 7 into it. And one more thing, c is here, ln is here, right? So what we will do right now is, now we know that the rightmost is not null, okay, and it is equals to some connection that is going to our current node, right? So we will add 7 into it, and we will also destroy this connection, because we don't want to change our tree, okay. And we will take this current to this end, to its right. We will take the current to its right now. So what we did, we visited from this to this to this, okay. We again went to this, and now we went to this. Are you seeing this? It is completely same as that of our Euler path, right? It is completely same as that of our Euler path. So this is how we are going to process in it, okay. This is how we are going to process in it. So let us do the same thing again, okay. Let us do the same thing again. So we'll mark it because it is again visited, right? So what we will do, our C is here, right? So left node will be placed here. We'll now find the rightmost, okay. We'll take out the left node first, okay, and then we'll find the rightmost, okay. And we will check first. We'll check if left node is not equal to null. If left node is not equal to null, then find rightmost, okay. So here left node is not equal to null, right? So find rightmost. Rightmost is this only, make connection. connection is not established, make connection. So I made a connection, okay, and after making connection, what I'll do, I'll shift this. So here a mark that it is visited first, and now as I'm shifting it to the left, always shift C to the left, okay, always shift to C to its left, because we always make the left call first, right? In the recursion also we always make the left call first, and if left call is not succeed, then we go to right call after printing, okay. So we will handle the right calls or the calls to the right by ourselves, okay. So now C will come here, okay, C is coming here, okay. So now left node is now null. So when the left node is null, we know that this left side is ended, so that means that this person is also included in my in order. So 5 will be added in my in order, okay. Now 5 will be added in my in order, and now I'll go to the right, okay, because left thing is exhausted, right? Left calls are exhausted, so I'll go to the right, and already a right connection is already been made, so I'll go to this again. This C. So this is with the third time, and C will come here, okay. C will come here, again place left node to this, okay. We placed left node to this. So this time I have seen that the rightmost node left, what we do, we check if left node is null or not. If it is not null, find the rightmost is the 5 only, right? Rightmost is the 5 only, then calculate the right of rightmost. So right of rightmost is pointing towards the C only. So when it is pointing towards the C, then this means that my child, that means this child can point to its parent, that means it can access its parent, but it is not possible, right? It cannot be possible in a tree. So what happened here, I made a connection by myself, okay. I made a connection by myself. So what I need to do, I need to add it, okay. I need to end this connection because I don't want to change my tree, okay. I'll end this connection, and this C will come this side now, will come to its right now, okay, will come to its right now. So when it come to its right, then it will again make a left node. So left node will null this time, okay, it is null this time. So when it will be null, what it will do, it will say that okay, it is the last person which should be added. So 11 will be added now. Okay, 11 will be added now. Now what I'll do is I'll shift this C, to its right. So 11 is added, and left calls are exhausted, so shift it to the right. So C will come here, right? C will come here, and now the connection is not ended. This is visited 2 times, okay. Is it visited 3 times or not? I actually forgot to write, but no problem, we'll see again. The left node will be placed here this time. Now we'll find, okay, one more thing, why am I writing this cross? Because I want to show you that how many times in this traversal we are visiting a node, a single node, how many times we are visiting, okay. I want to show you that. So if you will do it by yourself, then do it in the same way, okay, so that you can also see that how many times you are visiting a node. So C will come here, right? C will come here, and then this time ln will be placed here. Give me the rightmost. So it will say this is the rightmost. So right of rightmost. So right of rightmost is not null. It should be null. If it is the right of rightmost, then it should be null. But this time it is saying that right of rightmost is pointing to our current. That means it is pointing to its parent. It is not possible. So that means I made a connection. I have already processed this tree. When we see that a connection is already made, okay, when we visit a point where the connection is already made, then that point will be considered as the point where the left tree is being processed, okay. Here the left tree is being processed. So when the left tree is being processed, what I need to do, I need to end this connection, right? I need to end this connection, and then I'll add this 2 to my collection of in order, okay, to my collection of in order. And then after that, what I'll do is I'll take this to the right, because the left tree is already been completed. So in the 2 cases we move to right. In 2 cases. Sorry. So in right, 2 cases are, first is if left call is exhausted, okay, or there is nothing in the left call, exhausted. Okay, or second thing is if left tree is processed, left tree is processed, that means completed. If left tree is processed or there is no left call, then we come to right side. Okay, so we'll add to our collection, okay, of in order, and then we will take this C to its right. So here we have C. Okay, so it is visited 3 times and it is visited 4 times, and it will ln will go here to find the leftmost, right? So it is visited 3 times, and then again it will come here. So it is visited the first time right now. Okay, when it is visited first time, we'll place the left node is null. Okay, so when it is null, then it means that it will be the part of my collection of in order, so it will come here. Okay, and now after this, what I'll do, add it and make it right call. So go to its right. So I'm saying call, but I'm not using recursion. I'm showing you that how I'm going to do this, how I'm going to do this. I'll make some connections. Okay, and how I'm making this connection, you will see that in code. Okay, so this time this 5 will go to this, right? And then what will happen, the C will move to this. This is how 5 will move to 9, because the C will move. Okay, C will move, we'll place the left node here, we'll take out the rightmost. The rightmost of right is null. If it is null, make a connection. I made a connection. After making the connection, shift it to the left, so it is visited once, and then C will come here, so it is also visited twice. Okay, so now what will happen is, see, the left node is null this time. I'll make a left node, but that is null. So when it is null, then it is the part of my collection. So add this to my in order. So I added this to my in order, and now 9. Okay, what I'll do now is I'll shift it to the right, because left calls are completed, so shift it to the right. So right is this 9, right? Right call is this, so right will take it to 9 again. So it will again go to 9 twice. It is visited, then C will come here, so again left node will come here, and it is visited thrice. Okay, so it is visited thrice, and what will happen, so now left node is here, it is not null, so give me the rightmost. So rightmost is saying that right of rightmost is not null, it is pointing to current. So it is pointing to current, that means it is pointing to its parent, but it cannot point it to its parent in a binary tree. That is not possible. So I made this connection. That means I process that tree. I have already processed that tree. So when I have already processed that tree, then what I'll do, I'll add 9 in this. Okay, I'll add 9 in this. I'll end this connection from here. Okay, and then what will happen is, after ending this connection, I'll move to its right. So when it will move to its right, then its right is already null. So now it will point to null, current will be null. So when current will be null, we need to stop at that point. Okay, so this will be the in order. Is it same? Yes, it is. See, 2, 7, and then 5, then 6. 2, 7, 5, 6, then 11, then 2, then 11, then 2, and then 5, then 4, then 9. Okay, it is the same in order, but I haven't used recursion. How I haven't used recursion? See, let us see that in our code. Okay, I hope that this is completely clear. If it is not clear, then I request you to kindly go back and see this dry run, and if possible, you can do that by your own, because you can get the clarity by doing this dry run by your own. Okay, and the later part which is remaining, if some dots are remaining, then I'll cover those dots in this code. Okay, in this code. So let us go to the code now. Okay, so let us begin with the code. Okay, and let us see how we are going to code it. So in Java we are going to code it. So yeah, so here we have already managed the input and input for you. Okay, which you just have to complete a function that is this. Okay, this function we need to complete. So how we can do this? Same as we did in our dry run, right? So what I did in the first, tree node of current, right? And that was pointing towards the root first. So yeah, tree node, what is it? Okay, tree node, let us say it root. Yeah, the name is same. So let us say it root, and anything else that we need to change? No, that's all. So here I will return an array list as returning, right? We need to return an array list. So let us make an array list of integer. Array list of integer. Answer is equals to new array list. Okay, so this is what we need to do. So this is current, right? And we will do the work while this current is not equals to null, right? We'll do this work till then. So what we'll do, first of all, tree node, left node, right? Tree node, okay, not this, tree node of left node is equals to it was equals to tree node of left is equals to current dot left, right? So in the left I used to place at C. So it was like this. Current was here, left node was here. I was finding the rightmost from for it, right? I was finding the rightmost, and if the right of rightmost is equals to null, then make a connection. Okay, so this is what we were doing. So let us do the same thing. So we have find it what we have now. We have the left node, right? And we were checking first of all if left node is equals to null or not. Okay, if it is equals to null, then we will do something else. We will do something. See, if it is null, that means if current is here and left node is null, okay, left node will be here at null, right? If left node is null, that means this tree is already been this left side is already been processed, and when it is already been processed, then this person will be added to my in order, right? This person will be added to my in order. So let us do that. So what I'll do, when it is null, then at that time will answer dot add this current dot val, right? So I'll add this to my answer. Okay, and then the left call are being completed, so shift it to the right. So current is equals to current dot right. Okay, so this is what I'll do. And in else what we were doing, we were finding the rightmost. So tree node of rightmost node is equals to get rightmost node. Okay, get rightmost node, and that was get rightmost node, and we'll give it left node and current, right? Why I'm giving the current? See, we have this. That means if we are here, okay, if we are at this point, so my left node is here, right? So if this is pointing towards this current, right? If this is pointing towards current, then at that point only, then at that point also it is my it is my rightmost node, right? It is my rightmost node. So I cannot say that this is my right node, and if I'll not check this, if I'll not see that if it is pointing to this or not, then I'll say that this is my rightmost, right? This is my rightmost, and not even this, the right of this will make a cycle, or this will be the rightmost will be this, okay, or this, we can say the rightmost will be this. So we need to check at that point also when it is pointing towards the current. If it is pointing towards the current, we need to check at that point also that if it is the rightmost or not. So that is why we are sending this current also. Okay, so I hope that you got this reason. So after this, what we used to do, we check if rightmost node dot right is equals to null or not. If it is equals to null, then do something else, do something. If it is equals to null, that means that no connections are established. So make connections or threads, right? And else the connections are already being made, so destroy connections, destroy connections or threads, right? Destroy connections or threads. So how I'll do this, how I'll make the connection. For making the connection, what I'll do is right most node dot right is equals to current, right? I'll point it towards the current, and then what I'll do, see, I'll point it towards the current, and after this we used to do this. See, so when my left node is here, current is here, okay, then if there is no connection, we make a connection and we shift this to this, right? We shift this, so we will shift it, so what I'll do, current is equals to current dot, okay, shift to the left. So this time it will be shifted to the left, and the connection has already been made, okay. And now if the connections are already been made, see at this point, if the connections are already been made, then this will be the condition. Then this would be like C here and Ln here, okay. So connections are already been made, so what I'll do is I'll destroy this connection and add this, and will send it to the right, because this tree is already been processed, okay. So what I'll do, I'll answer dot add current dot val, okay, this will be added, and after that what will happen, we will shift it to the right and destroy the connection. So for destroying the connection, what I'll do is rightmost node dot right will be equals to null, and after that it will be equals to null, and again current is equals to current dot right, okay. We'll shift it to the right, yeah, it will be shifted to the right after adding it to our array list, okay. It is added to the array list, and anything else, yeah, this function is remaining. So public static, it will return a tree node, right? It will return a tree node. So tree node, and the name is get rightmost. So get rightmost node, okay, get rightmost node, and pass it tree node, left node, and tree node current, curr. So what I'll do is I'll check while my left node is not equals to null, right? I need to go to right, while my left node is not equals to null, and left node also should not be equals to, left node is not equals to what, current, right? Left node is not equals to current. If it is pointing toward the current, if the left node dot right, if left node dot right is not equals to current, and left node dot right is not equals to null, then at that point shift my left node is equals to left node dot right. So this is what I'll do, okay. So this is what I will do, and now in the end I'll return my left node, okay. So this is what we will do, okay. This will give me the rightmost node, okay. This will give me the rightmost node, and let us give it a run. So first of all, let me erase this, okay, and this will come here. So okay, let us give it a run to check if it is running or not. Some compilation error, return statement missing. Where is it? In line 46. Okay, I hope I know, yeah. So we need to return the array list, right? We need to return the array list. So give it a run again. Okay, accepted. Give it a final submit for all the test cases. Okay, beautifully accepted. So this is our code, and let us give it a final recap. So what we did, see, array list for storing the answer, and then tree node at the first we were placing this current, right? So this current for that, and while current is not equal to null, we will do the work, and we'll see if left node is, we will place a left node in the left of the current. Okay, every time we are placing the left node in the left only. Okay, so what we'll do, left node is equals to null, then we need to do something, and what is it? We will see when we have seen that when left side is being ended, at that point this condition occurs. When left calls are being ended, at that point this condition occurs. And second condition is for when left node is not equals to null. So at that point we find the rightmost node and we check if rightmost node is null, then we make connection. If that are not null, that means some connection are being made, so we destroy the connection and add that to our array list. So this is it. Okay, and one more thing, let us see this, that is the time complexity. The stars that I have marked here are for showing you that how many times is it visiting each node. So each node are visiting at least thrice. Okay, not at least thrice, I mean at least once, right? Because this is visited only at least once. So each node at on an average is visiting 3n times. Okay, so on an precise we can say the average time complexity is 3n, and if I talk in O, big O, then it is on. Okay, so that I mean, I hope that this point is also clear, the time complexity. Okay, and what I want from you, I want you to dry run this. Okay, I want you to dry run this code by your own to get the complete essence of this question, because the next question is also based on this. Okay, so we'll meet in the next video now. Till then, goodbye, take care, and don't forget to like the video and subscribe the channel. Goodbye.